All right, so the last section here in this chapter 8, section 8.8, is all about what's called improper integrals. So I kind of prefaced this in the last video about L'Hopital's rule or whatever. But basically, what improper integrals, I always thought it was named that. Where did they get that name, improper? What's improper about them? But whatever. So improper integrals, basically, the short version is they involve some type of infinity. So quickly, before we get back to what it actually means. Remember what a definite integral is all about, right? I mean, this whole chapter so far has been mostly about indefinite integrals, like how do you actually integrate something. Now we're going to get back to this definite integral idea, right? And if you remember, a definite integral involves the net area between the graph and the x-axis over some interval. Okay. Now, usually, all the stuff you've dealt with before with definite integrals, you had something that looks like this, right? Or some of it might be below or whatever. But there was definitely a finite bound here, a finite bound here, and there was nothing crazy happening in the middle. Meaning your function was continuous over that interval. That's what made it, Riemann integral they call it, and then you plug in the upper bound, plug in the lower bound, and you get what you get. Okay, for that finite area. Now, what improper integrals are all about is something about how the function works or the bounds themselves, there's some sort of infinity involved. Okay. So now when I say that, there's basically two types here. Okay. So improper integrals could be one of two types. One of which is obviously improper, and the type 2 is not as obvious until you do a little bit more digging into it. So type 1, the bounds themselves are infinitely large. Okay, so instead of going from some finite number A, some set number, to some other finite set number B, you could be going from A all the way to infinity, right? So what I mean by that is, remember, if you're talking about the integral from A to B, where this is set, you're starting here, you're ending here. Where something like this, what this is saying is you're starting at A, but your upper bound doesn't end, so it would go all the way. Now, the way I drew this picture, it's duh, right? I mean, what would the amount of area here be? Infinitely large, right? I mean, just the way this picture is. Look, the graph itself is getting larger. So if my bound never stopped, then of course the amount of area that you're talking about here is infinitely large. This would be kind of silly, but at least it gets the idea down. Okay. Same thing the other way. What if instead of going from A to B, you went from, think of it as kind of going backwards, or what you're really doing is you're ending at B and you're going down forever though. But again, your bound here is way over here. Okay. Or, oh crap, I read the negative, whatever. Copy and paste. But or you could be talking about going this way and this way forever. Okay. So you're one type of improper interval is when you have an infinite bound, whether it's the upper bound, lower bound, or both of them. There's some sort of, you're going forever in your interval that you're talking about. Okay. At first, those seem kind of silly. Like, why were we even talking about this? Because wouldn't that always be infinity? Well, no. Otherwise, why would we be talking about it? Otherwise, it'd be too easy. So we'll get there. Okay. But another type of thing that could be happening is kind of what I was talking about in the previous video. You could have, instead of an infinite bound, you would have some sort of discontinuity, or what's called an infinite discontinuity. Basically, it's a fancy name for a vertical asymptote. So now imagine you had some interval from A to B of f of x, and your lower bound itself is that, where that lower bound itself is indeed your vertical asymptote, right? So let's say this vertical asymptote happens to be at 2, and your lower bound is going from 2 to the upper bound, say 4 or whatever, right? So again, what we're trying to do is we're trying to find this area, but you have an issue here because I can't actually plug in A, right? Remember, you anti-differentiate, plug in the top, plug in the bottom, but the graph doesn't even exist at A, so how can I plug it in, right? We'll get there. Or you could have the upper bound is where your vertical asymptote is. So in this case, you're going from A, but then you're going all the way to B. But again, I can't actually plug in B because the function doesn't exist there. There's a vertical asymptote at the, damn it, too much copy and paste, upper limit of integration. Or you could have it somewhere in the middle. Okay, what I mean by, or not smack dab in the middle, but you could be going from A to B, like, so I don't know, maybe you're going from like 2 to 6, but there's a vertical asymptote at say 5 or 4 or 3 or something like that. So really what you're talking about is this and this. Okay, so the ultimate question is, what I want to know is whether or not these improper intervals, what's called converge or diverge, or in other words, is this a finite area, or this here, is this a finite area? Because they kind of lend themselves, especially the way I drew this one here. This is obviously going to get bigger. Maybe this gets bigger. I don't know. This one is just obviously going to get bigger, right? The way I drew it. Okay. But if this were to be a finite area, then you would say the improper integral converges. Okay. Now think about this one here. I mean, yes, this graph does go down forever, but it kind of lends itself to how I go about doing this in the aspect of, okay, if this graph were to go to that asymptote fast enough, right? In other words, it's so close that, yes, I mean, it never actually touches it. So there's always going to be some space here, which means there's always going to be some amount of area there. But what if it gets to that asymptote, or goes or approaches that asymptote so fast that it's virtually not there, okay? And then it would actually converge. So what does that sound like? Oh, you're basically talking about a limit, right? So that's why we did the last section with the whole L'Hopital's rules, because we're going to need L'Hopital's rule here along with the integration. Now, most of the time, you don't actually need L'Hopital's rule. You just need what I was talking about with the spirit of L'Hopital's rule, right? It's all about the rate at which things are going. If you have that appreciation of the rate to which things are going, then you kind of can do the limit stuff without actually using L'Hopital's rule. Sometimes, I mean, if you need to, you can, right? But anyway, what am I talking about? So the point here with all of these is you want to change the way you're looking at the problem in terms of going back to something I know how to do. What I mean by that is, let's say instead of going from A all the way to infinity, what if I went from A to, let's call B a set number, and actually stop it and actually go from A to some set number? But I want to leave this set number as an unknown constant, if you will. Okay. So basically what you're going to do is you're going to find a formula that you're going to go from some number to this other unknown number. Then we want to let that upper bound go off to infinity, right? It's kind of the same thing here. Pick a number, right, and set it in stone, but keep it as an arbitrary set in stone, right, an unknown constant, not a variable. Then we can perform the limit as it goes this way, right? And then this one's kind of the same thing. What you'd have to do is you'd have to do two of them, right? You could pick some number here, whatever this is, and then go from here to here, where this goes forever in this direction, and then do another one over here where this one goes in this direction. It'll make more sense when we look at the examples of this. Okay, so let's talk about this type 1 first with some actual examples first, and then we'll come back to this one idea here. But it's basically the same thing. All right, so, I wrote it on here, but just some terminology. So an improper integral is said to converge if all the corresponding limits converge to some finite number, right? So it'll make more sense if we do some examples. But you're going to transform these things into limits. If the limits converge to a finite number, then your improper integral is said to converge, and the improper integral would basically represent that finite area. Okay. If at any point in time you're doing these, your limits that you come up with do not approach a finite number, basically go off to infinity or negative infinity, then your improper integral is said to diverge, and your improper integral then represents an infinite area, right? So let's just check out some examples. Okay, so I want to determine if each improper integral converges or diverges. If it does converge, tell me what it converges to. Okay, just write it down. Now, you do not have to, but I would highly, highly, highly recommend, before you just jump into these, draw a picture. Okay, again, most of the time you don't have to, but it should at least kind of give you a feel of where you're going with this stuff. So what do I mean by that? Let's say I wanted to go from 2 to infinity. Now, first off, why is this an improper integral? Well, duh, because the bound is infinitely large. Okay, or in essence, what are we talking about here? So you're talking about this function x, or like, if you need to visualize y equals x. So what are we talking about? It's like a line, right? Where the slope is 1 and the y-intercept is 0. So basically you're talking about this, right? And you're going from, here's 2, and we are not stopping, right? So it's basically this area here. But I mean, this one's kind of, it's silly. It's kind of like it's just getting you used to this, the notion here, and also the notation. Okay, because think about it. If your upper bound were way over here at infinity, of course this is going to be an infinite area, right? The graph itself just gets higher and higher and higher. So the amount of stuff that's going to be here, if I never stopped, is going to be an infinitely large amount of stuff. Infinite area, then the improper integral here would then diverge. Duh. But just to kind of get the idea down, what I'm saying is when you do these, what you want to do is come in here and let's pick a spot. Right? But keep it arbitrary. What I mean by that is imagine B is a set number. I just don't know what it is. Okay. So basically what I want to do is I want to find this area. Or in essence, what I'm doing is I'm creating a new integral where I'm going from 2 to b. Okay. And then you just integrate this and plug in your bounds, right? So the usual stuff. In this case, the integration is pretty easy. It's x squared over 2, and you have your lower bound 2 and your upper bound b, right? Now I plug in my upper bound b, so it's going to be b squared over 2 minus plug in the lower bound. 2 squared is 4. 4 divided by 2 is also 2. Okay, so think of it as what I've done here now is by picking, it's arbitrary, yes, but imagine b is a set number. I just don't know what it is. Okay. So what I've done is I've created a formula that will give me the area from 2 up to some set number, right? So what I'm saying is if I wanted to go from 2 to 10, I could just plug 10 into here, right? 150, 48. Whether on that 10 squared, it's 100. Divided by 2 is 50. Minus 2 would be 48. So the area from 2 to 10 would be 48, right? Or if I wanted to go from 2 to, say, 3, right? You plug in 3 squared, it'd be 9 halves. Whatever, the 4.5 minus 2 would be 2.5. So the area from 2 to 3 would be whatever I just said, 2.5, I think, whatever. But the point is you've now created a formula that will give me the area from 2 up to this number. Now what I want to do is let's have that upper bound go off to infinity. Or now what I in essence want to do is let's do the limit as b goes off to infinity of this b squared over 2 minus 2 formula, which duh, if b is going to infinity, infinity squared is infinitely large, divided by 2, who cares? Subtracting 2, who cares? This would be infinity, so this would indeed diverge, okay? Right, so yeah, I mean, that's a relatively easy one to see, hopefully, but I think what the idea here is what you're going to do is you're going to translate your infinite bound into an arbitrary but set in stone finite constant. You're going to integrate, plug in the bounds, and you're going to create a formula. Then you're going to let your unknown constant go off to infinity. And then that'll tell you whether or not you have an infinite area or not. Okay. Now, a couple other things. This also kind of goes into just, okay, let's use our brains on this for a second, right? If the graph itself just keeps going up and up and up, then of course, it's always going to be an infinite area. So the only way this thing could ever even hope to have a chance of converging is basically the graph would have to go to 0. Right? Keep this in mind because this is going to come up a lot here and also in subsequent chapters later. I mean, think about that. If you're, don't forget what you're doing here. Remember what a definite integral, remember those whole rectangles with the Riemann sum deals? You're adding up a bunch of rectangles. So if you're going out to infinity, you're adding up an infinite number of rectangles. What's the only way an infinite number of rectangles could add up to not infinity? The only way that could happen is the things that you're adding are so small, they're virtually not there. Right? I mean, that would be the point. I mean, like, imagine like throwing cups of water in the ocean, but what you're throwing in is getting smaller and smaller and smaller and smaller and smaller until eventually you're throwing in these little tiny droplets of water. Are you really changing the amount of stuff that's in the ocean water-wise? No. That's so, but imagine you kept throwing buckets in, buckets and buckets and buckets, and the buckets are getting larger. Of course, the size of the ocean is then eventually going to get larger, right? So what am I talking about here? Let's check out a different one. So let's say I went from 1 to infinity of 1 over x dx. Okay, now here, again, you don't have to, but I think it's probably worth checking out what would the graph of this look like? So remember 1 over x, think of it as if x is getting closer to 0, 1 divided by something getting closer to 0 would then get larger, so there's a vertical asymptote at 0, right? And a non-removable discontinuity. But if x is getting larger and larger and larger, it's going to approach the x-axis. And the same thing would happen on the other side. Not that I really care, because what we're trying to do is from 1 forever. So now, think of it as if this is an object, and that's going forever. In other words, what's the perimeter of this object? It's infinitely long, right? Because I mean, it's literally going forever this way. Okay, so now the question is, yes, the graph is going to the x-axis. In other words, the heights here are getting smaller and smaller and smaller and smaller. Or think if this were like a Riemann sum, bunch of rectangles, the rectangles are getting smaller and smaller and smaller. But the question is, are they getting small and fast enough? Right? There's that whole L'Hopital's rule, right? It's all about going, but it's also about going fast enough, the rate. Anyway, so we'll get there. But the point here is what you want to do is think of it instead of going to infinity, relabel it as some set number. So I know what it is. So I want to go from 1 to, think of it as B, where you're actually stopping. You're going from 1 to B, and you're stopping, okay? So now when I integrate this, well, again, relatively easy. This is just a natural log of x, and then you got your bounds 1 to B. Plug in the upper bound, which is B, minus plug in the lower bound, which is 1. And this is natural log of 1 is 0, so this goes away. So ultimately, you're left with whatever the natural log of B is, right? Which in this case, I don't really need the absolute value, because if you're going from 1 to infinity, you're going from 1 to infinity. All these are positive, so you know B is positive, so you don't even really need the absolute value here. But whatever. The point is this area, if I wanted to stop at 10, would be natural log of 10. If I wanted to stop at 1,000,000, it'd be natural log of 1,000,000, right? I know it's been a while, but that's kind of where this whole thing came from to begin with. But anyway, now what I want to do is I want to do the limit as that upper bound B goes off to infinity, right? So it's the natural log of B as B goes off to infinity. Now, again, if you remember the natural log, yes, it's incredibly slow, but this still goes off to infinity, right? Remember, natural log looks like this. It's just really slow. But if you go off this way, the graph is still going up. It's just really slow. It still diverges. So yeah, it's understanding how the notation works and all this stuff, but it's also the larger picture of, okay, the only way these, with an infinite upper bound like that could have a chance is the graph would have to go to 0. This one goes to 0, but it doesn't even go fast enough. So we got to come up with something else. Normally in class, this would be a great thing. Okay, what do you guys think? What could I do? And most of the time people do come up with the fact that, well, if I want it to go to 0 faster, you need to make the bottom bigger, right? Right? The faster I make the bottom go to infinity, the whole thing is going to go to 0 faster. So let's try 1 over x squared, which you can check out on the calculator. It virtually looks exactly the same as 1 over x, right? It's just that it's going to go a lot faster. It might even be worth doing something like, I can never draw that right. There we go. Okay, so think of it this way. They both have the same basic shape. It's just that the 1 over x squared is going to go closer to the x-axis faster than 1 over x would, right? But they have the same overall basic shape, okay? So you could do the same basic idea here. I need to go from 1 to b of the 1 over x squared dx, okay? Now, first off, I don't know, it's up to you, but I would imagine you might be able to at this stage do this in your head. But remember, this is not a log because it's got a power of 2, right? It's not linear, so you can move it up. And then when you add 1, this is going to be x to the negative 1, and then divide by negative 1. It's basically going to make it negative. You're going from 1 to b. And it might help to think of this as like maybe negative 1 over x first, right? Put it back down in the denominator, right? So that now when I plug in my upper bound, you're looking at negative 1 over b minus negative 1 over 1. I don't know why I put parentheses here. You really don't need it. But ultimately, you're left with negative 1 over b plus 1. Negative 1. Right? Now you can do the limit as that upper bound b goes off to infinity. Right? So again, all we're doing here is we are integrating like you normally would, sticking the upper bound, sticking the lower bound. It's just that in this case, the upper bound happens to be an arbitrary but set number. Come up with a formula, then let that upper bound b go off to infinity. Which in this case, now, if b is going off to infinity, this is going to go to 0. And this isn't going anywhere. This is 1. So ultimately, this would indeed converge to 1. Now, I mean, think about that. This is an absolutely crazy result, right? It's like, okay, yeah, you get an answer, blah, blah. But seriously, use your brain on this for a second. What is this saying? The problem that we just did, 1 over x, yes, the graph itself goes to the x-axis. So it's basically like adding nothing when you go out far enough. But is it going fast enough in order for this to converge? No, it's not. Is 1 over x going to 0? 1 over x squared, is this going to 0? Yes. Is it going fast enough? Yes. Not only is it going fast enough, but the actual amount of area is 1, right? I mean, that is an absolutely insane result. Think about that. So what are we talking about, right? Remember, here's 1, right? And you're going forever, right? So literally, this is a graph, right? It's over here. I mean, it's barely right above the x-axis, sure. But this picture here, think of it as it's an infinitely long object. So this is something that has perimeter of infinitely large, right? It would literally take you forever to walk around this. You could never actually walk all the way around this object. Yet, how much stuff is actually inside of it? Only one. And that's nuts, right? So not only is it going this graph going 0 faster, it's going way faster because this one didn't even work at all, where this one definitely worked and it's even in a relatively small area, right? Crazy how that works out. Okay, so let's try a different one. Um, okay. You could graph this on the calculator if you would like, right? But one thing that you might want to be able to get in the habit of doing is just by looking at this, you probably could hopefully maybe graph it faster than it would take to graph it on the calculator. I don't know. Maybe it's just me. But think about it in terms of what's happening over here. Well, these are big positive numbers. If I take positive numbers, something positive squared is positive. E raised to, oh, now it's going to be a negative number, right? But what does E raised to a negative number mean? It's really on the bottom. So that means we're taking something positive and dividing by something else positive. So the whole thing's positive. So over here, the graph would be all up here, okay? And it's never going to hit 0, right? Because, I mean, as long as I don't plug in 0 here, I'm never going to hit 0. And this is never going to be 0, which means the graph is entirely up here. Also, you're probably thinking, yeah, if I take like 10 or 100 or a million or whatever and square it, this is going to be pretty big. But this is going to be way bigger, but on the bottom, which means you have a big divided by really, really big, which is going to make it small. So basically, what have we got? The same basic shape, right? Okay. Now, over here, some weird things might start happening. You're not sure, maybe. I mean, like, in this particular case, could you actually, I mean, like, is there going to be an asymptote over here? No, because this one doesn't have a division of 0 anywhere, right? I mean, because so this one would actually hit here, and then basically it's going to go up and then come back down, right? Again, how do I know that? Just play around with it, you'll see. I mean, heck, you can take the derivative of this that equal to 0 and find out there's a maximum there, but whatever. But think of it as almost like at 0, this is 0, so it's got to hit 0. This is e to the 0 is 1. That's not going to do much, right? So for small values of x, this is going to take over, right? But eventually, once I get to big enough values of x, this is now going to be so much bigger in the bottom that it's going to pull everything back down, right? You can check it on the calculator and see. I don't know exactly where the 3 is in reference to that. So what I'm saying here is, right, I'm just looking at x squared e to the negative x, right? So if I look at the graph of this, see how it kind of goes up and then comes back down. So somewhere in this general region, here's 1, 2, 3. So it's a little bit after. So exaggerating it a little bit, it's here that we're looking for, and we want to find this. Right, I mean, you can zoom in and see it, but it's a little bit after where the maximum is. I mean, so you can go through that whole, first derivative test to find out where that max is, but that's not the point, okay? The point is I got this basic picture. Okay, so now you're thinking, okay, the graph is definitely going to the x-axis. The question is, going to go fast enough? And if you really got the punchline of L'Hopital's rule, you should be thinking, yeah, this is going to go way fast enough. Yes, x squared is going to make this thing go up, but this is going to go way faster, which is going to pull it down really fast. And so, yes, this should zoom right towards the x-axis, right? Because exponential is way faster than this measly polynomial. Okay, so you're probably thinking, yes, this should converge. Okay, before we even jump in. Okay. Now, how do I do this? Again, what we're going to do is imagine stopping at some spot, and we're going to find a formula that would give me the area from 3 to some stopping point, and then later let that stopping point go up to infinity. Right? So what I'm really looking at is 3 to b of x squared e to the negative x dx. Okay. So now it might help to also, I got some bounds. So maybe let's ignore the bounds and let's just do the indefinite integral, and then we'll come back to the bounds, right? Because the number one thing is, how do I integrate this? Which this is a good section to end with as well. Not only because it's got improper, but it's a nice recap of all the different integration techniques that we've talked about. Okay, so we're running through the progression, right? You have a multiplication here. This is definitely streaming by parts, right? It's not a U substitution, right? The derivative of one piece is not the other, and vice versa. It's definitely not a trig substitution. It's not partial fractions. It's streaming by parts. Also, when you see this, hey, look, you have multiplication, and you're probably thinking by parts. Think, okay, One of them I want to take the derivative of, and one I want to integrate. Well, it doesn't matter this one, whether you differentiate and integrate, you're literally going to get the same thing, right? But this one, integrate would get worse. Differentiation would be better. But wait a minute, if I take enough derivatives of this, it's going to go away. So this is screaming not only by parts, but the tabular method might be the best way to do this, right? So the tabular method, remember, you got your differentiation column and you got your integration column. So we're going to differentiate x squared until it goes away, right? Then the other one, we want to integrate. But the integral of this would be itself, but then chain rule, or really undoing the chain rule, you want to divide by the derivative inside, but that would just be negative. Do the same thing again, but then divide by a negative, it's going to kill that negative. Do the same thing again, but then divide by a negative. And then don't forget your plus, minus, right? So then remember you got cross, cross, cross. So what do we got here? You got x squared times negative e to the negative x. So it's basically just going to be negative x squared e to the negative x minus 2x e to the negative x minus 2e to the negative x, right? And your bounds are now 3 to b. Okay. Now the whole reason why we're doing this is we're going to plug b into here, but then I want the limit as b goes to infinity. So you can kind of do this at the same time if you want. So what I'm saying is I want to do the limit as that upper bound b is going to go into infinity. When I plug that in, you're going to get a negative b squared e to the negative b minus 2b e to the negative b minus 2e to the negative b. Right? So there's my upper bound plugged in, and ultimately then I want to create the limit as b goes off to infinity. Minus, now plug in the lower limit. Well, if I plug in the lower limit, you're going to get basically negative 9 e to the negative 3 minus 6 e to the negative 3 minus 2 e to the negative 3. Okay, now here, this is really the reason why we did L'Hopital's rules for something like this. You're like, oh my God, b is going off to infinity. So what do we got here? Well, going off to infinity, this is going to be infinity squared, but negative. So this would be negative infinity times this is going to infinity, but it's a negative power, which means if this is going to negative infinity, then this is kind of like in the denominator, so this is really going to go to 0, right? The same thing here, this is going to be, well, really negative infinity, and this again is going to be 0. And this is basically negative 2 times 0, okay? So this one is obviously going to go away. These, remember that infinity times 0, it depends. Now, again, if you got the spirit of L'Hopital's rule, you could just look at this and say, hey, wait a minute. This piece is going to go to 0 way faster than this piece. This is going to take over. This piece is going to go to 0 way faster. This piece goes to infinity. This is going to take over. So indeed, these would all be 0, right? Again, if you don't see that, you could actually do this as negative b over, it's negative b squared over e to the b, right? That's what it really means. Now, if b is going off to infinity, this is indeed negative infinity over infinity. And you could use L'Hopital's rule then, right? This would be negative 2b over e to the b. Still negative infinity over infinity. You have to do it again, right? But eventually, hopefully you can see, yes, the top is going to go to infinity, but the rate is nothing like the rate at the bottom. So again, using the spirit of L'Hopital's rule, you can see 0, 0, 0. If you need to, go and actually do L'Hopital's rule, but hopefully at this stage we don't need to. But anyway, all this is basically going to be 0 minus this, but this is just a number, right? They're all like e to the negative 3, right? So we got negative 9 of them, negative 15, negative 17. So basically this is negative 17 e to the negative 3, or 17 over e cubed. Right? It's positive, and then you just move it back down if you want it. But you can see it is just a finite number. In fact, it's not even that big, right? I mean, what is 17 divided by e cubed, right? 17 divided by e cubed is less than 1, right? So, I mean, this decimal turns out to be 0.846, which I don't really care about the decimal. But my point that I'm trying to make here is if you look at the past one here, yeah, there's an x squared on the bottom, and not only did it go to 0 fast enough to create an area, the area was only 1. This one here, I think this helps to hopefully solidify how fast an exponential moves. Think about that. If I give, you're going off to infinity. If I plug 10 squared, you're already at 100, right? Plug in a million squared, that's huge. But this is going so much faster that not only does it counteract this getting larger, that it goes so much faster, so much quicker that it's able to go to zero fast enough to make this be a finite area, and it's not even that big. It's less than 1, right? That's how fast an exponential goes. Okay. Well, I don't know. I can't help it because it's already on the tip of my head. So later on, the next, not this next chapter, but the chapter after that, that's going to come back up. So I hope you're probably asking, oh, is an exponential the fastest thing? Almost. There is something that's actually faster. We'll get there later. But it's almost the fastest thing. Okay, what about 5? Yeah. What if I wanted to do 5 to infinity of negative 10 over x squared minus 3x minus 4? Okay, hopefully you can see, oh, it's the same idea. I got the upper bound is infinity. The main thing here is how do I integrate this? Okay. The other thing is also you probably want to have an idea of what this thing is doing. So hopefully you're probably thinking, well, where's all the action? The action is in the denominator. Right? There's no x on the top. The action is on the bottom. So yes, this would be infinitely large. Technically you're subtracting, you're taking stuff away here that's going off to infinity, but that is x squared. No, it's nothing like an exponential for sure, but it's still going to be larger or growing faster than this. So eventually this is going to take over. So eventually once you get out far enough, it's going to behave like a negative over something positive. So it's going to be a negative number, but going to 0, and it's going to behave like 1 over x squared, right? Because that's the main action, is that x squared. Since 1 over x squared converged before, you're probably thinking this one is going to converge as well. Okay? So the action is at the bottom, much bigger. Basically, the punchline, and we'll see this a lot more later, is as long as the power is bigger than 1, right, then there's enough stuff happening in the bottom to cause the whole thing to go 0 fast enough in order for these to converge. Okay. But the other question is, how the heck do I integrate this? In the process of integration, it also helps that maybe I understand what the graph looks like. What I mean by that is, well, I know it's kind of relatively new, but if you look at that, that's screaming factor to the bottom, right? So it's screaming, hopefully, either completing the square, actually you could, or, just factoring it if it does factor, and then using like partial fractions, right? So what I mean by that is, like, if you look at the bottom, you got x and x, got to multiply to 4. I mean, most people would probably try 2 and 2 first, but 2 and 2 is not going to add to 3. But 4 and 1 would, as long as the 1 is positive and the 4 is negative, okay? Which, doing this, I probably shouldn't be a little more diligent with this, because what is this telling me? When I factor the bottom, that means negative 1 would make my denominator 0. So over here at negative 1, the graph would indeed have a vertical asymptote there. And also at 4, there would be another vertical asymptote, right? Now, as far as what I'm saying is, in the general context here, would you have to worry about that? Yes. We haven't talked about that yet, but remember, vertical asymptotes can cause its own improper integration problem, okay? Because remember, the graph is shooting up or down following the asymptotes. But for this particular problem, it doesn't matter. Why? Because you're going from 5 to infinity. So 5 is over here, right? Now you might be thinking, oh, so the graph's up here. Well, it's not. Right? Think about that. There's a negative here, right? So the main thing is, like, imagine a number that's big enough over here, right? If I pick a number that's big enough over here, the bottom's going to be a positive, but the top's a negative, which means the graph would have to look something like this, right? Where it's approaching the x-axis, but it's underneath it. And then over here, there's a vertical asymptote. But again, remember, we're only going from 5. So what we're talking about is this area here. Right, you can graph it on the calculator and see, and you can see some other stuff. I mean, there's more graph over here, there's more graph over here, but as far as my bounds are concerned, who cares, okay? But again, it's ultimately the same thing. I want to think of it as I want to cut it off here first and find a formula to go from 5 to b, then let b go off to infinity, okay? So the plan is to go from 5 to b, and then, let the b go off to infinity. But before I do that, we got to integrate this thing, right? So hopefully you're already thinking, oh, this means I got to do the whole partial fractions deal first, right? So I got to do the partial fractions deal here, meaning, split this up into x plus 1, and this is x minus 4, right? Okay, where this is linear on the bottom, so constants. So then what does that mean? This means that negative 10 would have to equal a times x minus 4 plus b times x plus 1. Right? When there's only 2, you can just cross multiply like that. It's not really cross multiplying, but it kind of looks like that. Or just multiply through by the common denominator. X plus 1s go away, so you got a times x minus 4. Here, the x minus 4s go away, so you're left with the x plus 1. Now, again, you can just line up your constants here, because it's not that hard, right? Ax plus bx would have to, basically a plus b would have to be 0 because there are no x's. And the constant negative 4a plus b would have to add up to negative 10. You can create that system, right? It's up to you. Or since they're non-repeating linears, the quickest way, you could just pick values, right? Remember, you could pick, like, say, x equals 4. Because if I pick 4, then basically this is saying that negative 10 is equal to a times 0 plus b times 5. Right? I mean, the whole reason why I picked 4, so this goes away, and then I can just solve for b, because then b would be negative 2, right? Because a times 0 is 0 divided by 5. And you could do the same thing if you were to, say, pick x equals negative 1. Because if I pick negative 1 now, right, this is still negative 10. This would be a times negative 1 minus 4. But the whole point is then this would be b times 0, and it goes away. Or in essence, you got negative 10 equals a times negative 5, so then a would now be positive 2, right? So coming back here, you got a is 2, so you're looking at 2 over x plus 1, hold on, and then plus b, which is the negative 2 over x minus 4. All right, so this is what I'm trying to integrate. A is 2 over x plus 1, plus b, we just figured out was negative 2 over x minus 4. Okay, so now I got my fraction split up. Now you can integrate, but this is just going to be 2 natural log of x plus 1, right? It's a nice linear term in the bottom. Term of the inside is 1, so I don't need to adjust. Same thing here. This is minus 2 natural log of x minus 4. Term of the inside is 1, so I don't need to adjust. Now, normally you would do plus c and you're done. But remember, we are trying to do an infinite going from 5 to, oh, I can't do that. Go to b first, right? So what I want to do is go from 5 to b. Okay, so now we can plug in the upper bound, right? When you plug in the upper bound, you're looking at 2 times the natural log of b plus 1 minus 2 times the natural log of b minus 4, right? There's my upper bound. Minus, then plug in my lower bound. This is basically going to be 2 natural log of 6 minus 2 natural log of 1, right? So plug in the upper bound, plug in the lower bound, subtract them. And you can do it now if you want, but remember what we're trying to do ultimately is now do the limit as b goes off to infinity. Okay, so hopefully the only thing that I really care about now is this is the b stuff that's going off to infinity minus this is a number. Okay, so this is just some number. It is what it is. So the question is whether or not does this converge to a number or not. Okay, all right, so direct substitution it in. If I plug in infinity, infinity plus 1 is still infinity. Natural log of infinity just gets bigger. Same thing here. Infinity minus 4 is still infinity. Natural log is infinity. Right, so I got an infinitely large here and infinitely large here. But wait, you have a minus in the middle here. This is infinity minus infinity. What is infinity minus infinity? It depends, right? So it goes back to that whole spirit of L'Hopital's rule. Which one is going faster, right? If this one is going to infinity faster than this one, this would take over and go, then the whole thing would go off to positive infinity. We just get bigger. If this one were going faster, then this one would take over. It would get bigger, but it would be a negative number now, right? Or maybe they're going at the same rate. If they're going at the same rate, then they're going to collide together, maybe cancel off completely and go to 0, or maybe they're going to converge to 2 or 8, right? So again, whenever you have one of those indeterminate forms, it's either going to cancel off completely, right? One's going to take over completely, or they're going to collide somewhere in the middle, okay? So that's the question. What happens here? Well, if you think about it, I mean, what is the main thing that's causing this to go off to infinity? The natural log. What's the main thing that's causing this to go off to infinity? Natural log. So what does that mean? The main thing that's causing it to go to infinity, the rate-wise and the rate-wise, are the same thing. So they should indeed just cancel off. Should. But how do you know? Oh, L'Hopital's rule does not apply here, right? Because you have infinity minus infinity. How do I use L'Hopital's rule? I need a fraction. Well, great. You have a subtraction of a logs. How can I rewrite a subtraction of a logs? With one log where you are subtracting the insides, right? And that's the key here. It's all about when you have one of those indeterminate forms, you got to switch it. hold on. So, well, whatever. Let me just. So I got the limit as b goes to infinity. Now, I probably should preface, make sure before you use that subtraction of logs, there are numbers out front. So technically there is a power of 2 here. Okay, so what you're really talking about is the natural log of b plus 1 squared divided by the b minus 4 squared, isn't it? Yeah. So you're bringing these powers, you're bringing the power of 2 up, then subtraction of 2 different logs, you're putting it together, where you're talking about 1 log, where you're dividing, right? Minus, and then over here, this was some number. We'll come back to that later. I don't care about that right now. We'll come back to that, but that was some number, okay? And so now the key here is you're taking the natural log of this whole thing. But since this has a squared and this has a squared, I could think of this as the natural log of one big fraction, b plus 1 over b minus 4 squared. And then I want to find the limit as b goes off to infinity. Okay. Now, technically, you have the top is going to infinity, the bottom is going to infinity. So this is like infinity over infinity squared, then take the natural log. But, man, I don't know. Maybe it's just me. But again, could you use L'Hopital's rule on just that part of it, right? Take the derivative of the top, the derivative of the bottom. So, I mean, it's kind of like you're kind of going off to the side and doing that limit. But, dude, seriously, just look at it. It's going to 1, right? The top and bottom are exactly the same. So this is going to go to 1. So this is going to behave like, well, I probably should do this. The red being what it behaves like. So this is going to behave like natural log of 1 squared, which is going to behave like natural log of 1, which is going to behave like 0, right? This red, what I'm talking about here, is approaching, right? This is going to approach 1 as b goes off to infinity. Because basically what's happening on top and what's happening at the bottom are exactly the same, right? Once you go far enough, who cares about 1 and minus 4? 1 squared is still 1. Natural log of 1 turns out to be 0. So this whole thing basically is going to approach 0. Okay, or it has that nice feel that they're canceling off. Okay, but now we still have this other number to worry about here. So we got, hold on. This number, let me just rewrite this. You got 2 natural log of 6 minus 2 natural log of 1. Okay. So this part happened to go to 0. Over here, we just have this part. But the natural log of 1 again is 0, so you're just left with 2 natural log of 6. But so basically it's 0 from here minus 2 natural log of 6, which, you know, you can just leave like that. Or if you wanted to, you could get a little fancy and you could think of this as the natural log of 1 over 36. Right? I mean, I don't really care. But I just do it, you know, because I think of 2 as a power, right? So it's 6 squared. And since it's a negative power, you can put it back down. Whatever. It's up to you. Or just leave it like that. Right? But either way, you're going to get that. I think this way might be better only because e raised to what number is going to give you a 6? Bigger than 1. Multiplied by 2, bigger than positive, basically. So my point is, this is a negative number. So it should make sense in terms of the problem. So what is that saying when you go back to the picture? Oh, look, it's all below the x-axis. So that area, you know, the definite integral better report that as a negative number, right? Because it's below. Okay, and even relatively small, right? I mean, if you did the 2 natural log of 6, right? It's not even 4, right? So that area is not even 4. So it kind of goes back to what we were saying. Is the bottom going to infinity fast enough to cause the whole thing to go to 0 fast enough? Yes, it is. Okay. All right. Let's leave that. Keep going. So let's try 6. So with 6 now, we want to go the other way. Okay. So now we're going from negative infinity to negative 2 of this crazy looking function here. Again, this is also kind of a good summary of some old algebra stuff, I guess, of knowing what these things look like and how they behave before you actually get to the integration. Right. So what I mean by that is visualize, okay, we're going from negative infinity to negative 2. So graphically speaking, I only care what's going on over here, right? Because you're going from negative infinity to what's going on at negative 2. That's my main interest. Okay, so let's kind of play around with this thing a little bit. You know, you could graph it and see, but things like, okay, first off, when in doubt, things you can do quickly is, does this thing ever hit the x-axis, just to kind of get an idea of what this thing looks like? This is never going to be 0. This is going to be 0 at 3 halves, right? Move the 3 over, divide by 2, it's 3 halves, so which means it's going to hit the x-axis somewhere over here, okay? Now, generally speaking, if I were to pick big x values over here, right? big x values, minus 3, squared it. This is going to be a positive. This is going to be positive. So the graph is somewhere up here. Okay. And hopefully you're probably thinking, hey, this e to the x is going to take over, which means it's going to shoot up really fast. Right? Okay. Now, what's going to happen on the other side? Now, once I maybe think negatives over here. If I pick a really big negative, right? This is going to be a negative. Subtract this. This is going to be a negative. But now this is a positive. So this is a positive here, right? So this is a big positive here. Okay. This over here is going to be e raised to a negative number, which now means it's going to be, a positive number, but this is kind of like on the bottom, right? Because you're plugging in negatives. So hopefully you're maybe thinking something that looks like this. I know it's tricky at first to see, but at least all positive, always positive, no matter what you're plugging in, right? I mean, here, this is positive, this is positive. So the graph is basically never going to be below the x-axis, right? It hits here. So what would have to happen is it would have to look something like this. Now, where this max is, I don't know, but it would have to look something like this, roughly, right? So, you could, well, what the heck, we're already here. Okay, so 2x squared e to the negative x. So you can see eventually it's coming. Oh, it's just way off the screen. So, right? Okay. Oh, I was going to say, that does not look like I was expecting. I typed it in wrong. I'm like, what the heck? It's on the wrong side. Well, duh, because it's e to the x. I typed in e to the negative x. Did that to make sure you pay attention. No. Okay, there we go. That's what I was expecting it to look like. Okay, but you can definitely see it hits right there at that. That's a 3/2 I was talking about. The e to the x takes over here, right? For small values of x, think this is relatively small. This thing is going to have the power, and that's kind of why it looks like a parabola right in here. But then for really, really big negative numbers, e to a really, really big number is now in the bottom, which means this whole thing is going to go to 0 really fast, which hopefully, again, you're thinking this probably should converge, right? So again, what we're going to do here is call this B. The only difference is now this is going to go this way, okay? Or come back to the bounds. Basically, we got to integrate this thing first, right? So especially when it's more complicated like this. Forget the bounds. We got to worry about the whole integration. All right, so how do I integrate this? Again, polynomial times exponential. This is screaming by parts, or in this case, especially tabular method would be great, right? So you can, I probably should write that. So we're talking about the by parts, not only that, the tabular method, right? Because if I take enough derivatives, the polynomial is going to go away. This one's never going to change. So I got a differentiation column, I got an integration column, right? So the thing I'm differentiating is a 2x minus 3 squared. All right, so the derivative that, well, okay, let's do this. I think we've done enough derivatives at this stage in your life, right? The 2 would come down, but then chain rule, you have to multiply by another 2, so it's really going to be a 4. You could distribute this in now or do it later, but eventually the derivative of this is just going to be 8, right? And then the other one, when you integrate it, is never going to change. Plus, minus, plus. All right, now we can cross. So you got the 2x minus 3 squared e to the x minus, whatever, it's up to you. Let's leave it. 4 times 2x minus 3 e to the x, right? You could distribute the 4 if you wanted here, whatever. So you got these times each other minus these times each other. But now we have bounds. In this case, I want to think of my lower bound as being set in stone. I just don't know what it is. Call it B. And then I'm going up to the one that's given -2, right? Then we want to do the limit as B goes off to -infinity now, right? Because that lower bound is going to -infinity. So think the lower bound, I'm just going to plug a number in. That's going to be a number, right? So I don't need to worry about this limit when I'm doing the upper bound. So if I plug in the upper bound -2, what is that? -4 minus 3. So it's like -7 squared e to the -2 minus 4 times -4 minus 3, still -7 e to the -2, right? Minus plug in the lower bound. But the lower bound is going to eventually want to go to -infinity. Oh, no, B. Sorry, I'm kind of cramming that in there, right? But just plugging in the lower bound. So it's 2b minus 3 squared e to the b minus 4 2b minus 3 e to the b. Okay. Now, again, what you might want to do is think, okay, b is going off to negative infinity, which means this is really think in your head, this is on the bottom. This is on the bottom. So you got a polynomial on the top. So technically this is infinity over infinity. But this exponential is on the bottom. This one's going to take over. The whole thing is going to go to 0. Same thing here. You have this polynomial on the top, technically negative here, and you're dividing by something that's going to go off to infinity, right? Because it's a negative power when you plug in negative infinity. But again, this one's going to take over, the exponential. So this is indeed going to go to 0. So basically, all of this is going to go away anyway. So all we're left with is that number, right? Which is what? 49 e to the negative 2 plus 28 e to the negative 2. Whatever that is. So 49 plus 28, or 77 over e squared. Right? But and again, that's that whole spirit of L'Hopital's rule, because technically you're supposed to write this as something over something, then use L'Hopital's rule. But seriously, at this stage, you don't need L'Hopital's rule. You can just look at that and see, hey, that exponential is going to go faster, goes away, right? Okay, so, but it has that same basic feel. It is going to 0, right, fast enough, right? So that's what's causing it to converge. It just happens to be going the other way. So what? All right, last one of this type. The difference with this one, you got both bounds are infinitely large. Okay, so I got negative infinity to infinity of 6 over 4x squared plus 9. Okay, which means now you're going both ways. Now, generally speaking, when you see something like this, going back to this graph, I mean, one number was usually given to you and you went the other way. One number was given to you, you went the other way. Here, you don't have anything to work with. So you don't have to, but the easiest way usually is pick something. I don't know, you want to use 0 or you want to use 10, whatever. Pick a number, doesn't matter, and then go from the lower bound going to 10, and then another one going from 10, for example, to the upper bound. Let me show you. Again, you don't have to, but it would definitely help to see what's going on graphically. Oh, sorry, I just kind of did it. But no, I know I want to go both ways, so I didn't really, emphasize one side or the other. But also notice, no matter what I plug into here, it's going to be a positive. So everything here is going to be positive, which means the graph is going to be above. Okay, right? So things like what you could do is get some nice numbers, like if x is 0, this is going to go away. So you're left with this here. So it's going to hit up here at 6/9. Okay, now think about that. The bigger x gets, the bigger the bottom is going to get. The smaller the whole thing's going to get. So it should go like that. But what's going to happen? The other side, negative numbers, are going to behave the same way. So it should look exactly symmetrical. So it should look something like that. Right? And again, if you follow me on that, great. If not, graph it on the calculator to help see 6 divided by the 4 x squared plus 9. Right? Actually, I don't need that other parenthesis. And you can see eventually. I mean, it's down here, but it's exactly, you can zoom in to see it. Okay. But again, hopefully you're visualizing what's really got to happen here is you have to split this up into numerous problems. What I mean by that is I need to go this direction and I need to go this direction, but I have to have somewhere in the middle. This one here definitely lends itself to use 0. So what I'm saying is it's almost like two different problems where I want to go from, think of it as going from my lower limit of a to 0 of this function, 4x squared plus 9 dx. And then eventually you're going to do the limit as a goes to negative infinity, right? So that would give me from the, so what I'm saying is what you're really doing is you're fixing a and you're going from a to 0, right? So I'm fixing this a to 0, but then eventually a is going to go up to infinity. Then I'm going to do another one where I'm going to go from 0 to, say, b of this 6 over 4x squared plus 9, right? So now I'm going from 0 to b. So I'm going to do this area, but then eventually I'm going to do the limit as this one goes off to infinity. So if this one is a finite number, it'll give me this area. If this one's a finite number, it'll give me this area. So then the overall finite area would be add them together. Now, if one of them converges and the other one doesn't, then who cares? The whole thing, it's like, one bad egg ruins the whole thing, right? So anytime you have a situation where you have to do multiple limits, which might happen, we'll get to that. Sometimes you might have to do more than just two. But anyway, anytime there's more than one limit floating around, if one of them diverges, you don't even have to do the other one because then it doesn't matter, right? Might be good practice, but as far as the integral converging or not, no way, right? As soon as one diverges, you're done. But anyway, now that we have the plan, either way, it does in fact hinge on this integral. Okay, so I would highly recommend, let's go out to the side, let's figure out what this integral is first, then we'll come back to this, then we'll come back to this, add them together. All right, so that's my plan. All right, so now it comes back to that stuff we were doing earlier in the chapter. How do I integrate this? Well, hopefully at this stage, this is screaming to you 2x squared plus 3 squared, right? So this is definitely like a trig substitution problem. Or at this stage, when you see that something squared plus something squared, there's nothing else happening, no root or anything else. This is basically going to be an inverse tangent, right? So remember, an inverse tangent is going to be the variable part 2x over the number that's being squared here, 3. That 6 that was out front is just going to sit there. And then remember, you got to divide by whatever the variable, that's the number part is, right? So the top is the variable part that's being squared. The bottom is the number part that's being squared. But wait, the inside part here, this is this. Remember, this is inside, right? So inside here, the variable part is not just x squared. It's a 2x that's being squared. So the inside is really a 2x. The derivative of that is 2. So that means you need an extra 1/2 out front, right? So think whatever number's here, that's what's got to go here and here. But there's an extra derivative of the inside. That's what this 1/2 is all about, right? All right, so there you go.